Hello guys, sorry for the late video on capacitance, but I figured I'll give everyone a bit of a rundown just before our test on Saturday. So I'm just going to start with the definition of capacitance, which is just in its very basic form, any two separated conductors, so they're isolated from each other, no charge can flow between them, and there is a charge stored on one of them and a negative charge on the other. So basically you just took charges from this neutral conductor and you put it on this one, or positive charge, or you take electrons from this one placed on this one. Doesn't really matter. Important thing to realize first of all is that since we have charge Q here and charge Q here, it might be tempting to say that, well, we are storing 2Q of charge, but we're not. We denote that with just Q, so just the one and the other. And the other thing is that the net charge is still zero. So if you take the whole system in this case, the net charge is still zero. So interesting thing to also note here is that we'll see that capacitance has everything to do with the electric field, of course, since the energy that's stored in a capacitor is stored in the potential energy of this field. So two important things. First of all, the more field lines we can get nicely connected like this, the better our capacitor is, basically, because this is kind of, you can see this is leaking away the energy. This might go to some interference or whatever. But so first things first, we need to make sure that we are convinced that the potential difference between these two things makes sense. Because we don't want some random definition such as the potential difference between the centers of these points. So we need to quickly just run through that. So since we have two conductors, we have already seen that the electric field inside conductors have to be zero. I've covered that in one of my videos as well to give a little bit of an intuitive explanation of that. But so if the electric field inside is zero, that means that I can basically take any path through this electric field, and when I integrate over that, the work done is zero, because our electric field is zero everywhere inside of it. So if I take from this point on the surface, and I take the word to that point of the surface, that's going to give me some potential difference, because that's the definition of potential difference. But if say I start at this spot, and I want to know what's the potential difference between this spot of the conductor on its surface and that spot. Well, we can actually argue that it has to be exactly the same, since we can take the integral through here, which is zero, then our initial integral, which was our potential difference the previous time, and then to here, which is zero again. So 0 plus potential difference by 0 is just that potential difference. So we can therefore see that the potential difference is a pretty nice concept to use here, since it doesn't matter how we precisely define it, since it's going to be basically a constant for these two conductors. That's also why it's important that they are conductors. We will also see that the concept of capacitance of such a capacitor will be useful later on repeatedly. So it basically gives us a way to relate the amount of charge stored in a capacitor to the amount of potential energy that is there. So it's just a nice way to relate these two quantities, and this is specific to a capacitor, so that's going to depend on the specific geometries, how they look, how close they are to each other, and what the conditions are. If it's, for example, air separated and you have a wet day, it's going to be different. So it just depends on your specific circumstances. Luckily for electronics, we usually use well-defined capacitors. That's going to be the same every time, because that would be quite not nice otherwise. The most common place you'll see a capacitor is in a circuit. I just want to help you get a feel for how it actually works. So a great way of thinking about a battery in this circuit, because this is just a capacitor. So thinking about the battery as basically just a source of potential difference, usually by chemical energy or whatever, we can quite easily see why this will happen. So we already saw the relationship between capacitance, charge, and potential difference, which you can also apply here. But we can also think about the negative part of our battery, of basically just pumping out negative charges or sucking in positive charges. Either way works. So if we just think of electrons flowing out of this the entire time, it's just going to go sit on this side. And so if it's just going to sit on this plate's going to get negative. But this plate is also affected by this plate. So if there's constantly a stream of negative charges being pushed here, they're obviously going to be pushed back by this plate a bit. But mostly, the negative charges on this plate is going to be repelled by it, because opposite charges repel, and the positive charges here is going to get closer to it. So this plate is going to get positive, and all the negative charges is going to get sucked up into the positive side. Or you can see it as the positive side pumping out a lot of positive charges and going to sit on here. And then what we see is we get two opposite charges here. They always have to balance because we have conservation of charge, and beforehand our entire circuit was neutral. So that means that all the charge that gets added here has to be get subtracted here, or vice versa. So we have to have the equal amounts on both plates. And that's just basically how a circuit charges a capacitor. It just creates this potential difference, and then it pushes it up here. So the nice way of thinking this is literally just this part of the battery pushing a lot of balls or whatever, and it's getting scrunched up in here, and the pressure is pushing them away on this side. Because the moment you take this away, say you just close the circuit here, then there's nothing pushing this anymore. So all that's going to happen is they want to get together, because this is negative and this is positive. They can't go over this gap. That's why there's a gap. So they're just going to flow through the rest of the circuit. They're just going to start going back again. And that's how you obviously get the work out of a capacitor again, when you discharge it. But yeah, so it's just nice to get that feel for literally just the potential energy of the battery pushing it in. And it has to be held there, because if it's not held there, and there's some way for the charge to flow, then it's just going to flow. And then you get the discharge of the capacitor, which is also handled later on. Now, for understanding how capacitors function in a parallel circuit, just to introduce the circuit, so we don't know what's going on in the rest, we just have a potential difference over this part. Then we can see we have two capacitors here in parallel. But we can see that not only is this a capacitor, since we have a gap, and then we have a potential difference over this, and we have a gap here and potential difference over this, but we can picture these entire halves as basically being two halves of a bigger capacitor, since it's also separated here and there's also a potential difference over this. Well, we know how potential difference splits over a parallel segment. We know that the potential difference over this part has to be the same as this, has to be the same as over the entire part. That's just high school circuits. So we know that V1, so that's for that one, equals that for V2, equals that for V, which is just what we measure over this entire thing, which is just the potential difference over the equivalent capacitor that we can imagine instead of this parallel part. So then we can also imagine all the charge that's stored here. So we can think of this plate. We say this is the positive side, so there's some charge Q1 for the first one that's stored on here, and there's some charge Q2 stored on here, and then there's obviously the negative minus Q2 here and minus Q1 here. Then we can also think of this entire half storing Q1 plus Q2, and this entire half is minus Q1 minus Q2. So then we can say that this equivalent capacitor has an equivalent charge of Q1 plus Q2. We just have a visitor here. So if we have Q1 plus Q2 here, then we can say we know the capacitance of some capacitor is just the total charge stored over the potential difference. But we have both of these values now. We can just substitute in Q1 plus Q2 for this total charge, and we know the potential is going to be the same for both of them. And then we know that also, since this is the potential over this component, and Q1 is the charge over this component, that's just the definition of capacitance of this component, which is a capacitor, so that's just C1. And for Q2 over V, we know that that's the charge stored in this capacitor for the potential over this capacitor, so therefore Q2 over V is just the capacitance of the second capacitor. So we get that the equivalent capacitance of such a parallel setup is just the sum of the two, which is very simple. Okay, so for a series circuit, we need a bit of a different view. It's not going to be quite as simple as that. So we can once again just think about these two capacitors and try to think about how they would act together. So the first interesting thing we can see here is there's a Q minus and there's a positive Q there. So if there's negative charge here and an equivalent positive charge here, then they're just going to attract each other until they spread out here in the center, and this entire thing is neutral. So we can almost ignore this entire center part here and just think about this outer part as being a giant capacitor. So for that capacitor we have V is the potential difference, which is the same as the potential difference of this plus the potential difference of this, just by normal circuits. So we have the V for this equivalent capacitor, and then we can see that since this part's ignored, we have two plates here that have stored Q and minus Q charge. And since we have two plates here that stores Q and minus Q charge, our effective charge stored is just Q for this entire equivalent thing, which is the same thing as the charge stored on this one and on this one. So then we can just say that the equivalent capacitance is just Q over V. That's just from our definition. But then we get this ugly thing that we can't really separate because we have a sum in the denominator. So if we invert both of the sides of the equation, we can then try to separate them, since we want the capacitance of 1 and the capacitance of 2 to be separate. And then we get this nice expression where 1 over the equivalent capacitance of this bigger capacitor is just 1 over the first capacitance plus 1 over the second capacitance, just because of how this math worked out. Just in case it wasn't clear, one way to motivate that both of these charges has to be Q and minus Q and Q and minus Q is just that we have to have conservation of charge. So this center part was negative before we connected a battery or some kind of potential source here. So it has to be negative in total afterwards as well, because there was no way charge could get to this isolated part. So the sum of these two has to be 0. And the same goes for the rest of the circuit. So the sum of these two plates also has to be 0. So then there's no other way for it to be than these charges being equivalent. You can work through the math, but I think it's quite easy to just see that from those facts. So lastly, I just want to look at potential energy. So starting with two charges, the case we know, we have this definition for potential energy. So I have two main ways of interpreting this. One of it, first of all, we need to notice that there's no 2 factor here. So that's the thing that the notes want you to realize, is that it's not the potential energy of this due to this plus the energy of this due to that, which is an important concept to grasp. Because what we have here is the potential energy of the system as a whole. So a nice way of thinking about this is, first of all, the one you'll see in the notes as well, is the amount of work it takes to take this one charge from infinitely far away and move it to this place. If you do that calculation, this is equivalent to the amount of work that you need to have done to put this charge here. So because basically you put work into the system, so it has to be stored somewhere. That energy doesn't just disappear, so it's stored in the field. But another way is thinking about the reverse of that, and that is if I let these two go, then they're going to start speeding away from each other, right? And the potential energy that's stored in that is the same as the kinetic energy that these will have if they're infinitely far away, because they'll keep accelerating each other out. So it's basically the maximum kinetic energy that this system can reach as a whole. So this kinetic energy plus that one's kinetic energy. It'll also just happen if you keep one still and the other one. It's going to be the same thing. So that's the way of interpreting what this potential energy is, because it's some energy that's stored in the electric field itself. It's very abstract, but just thinking about the way that you put energy into the system and it can't disappear, and equivalently, if I let go, this system's going to gain energy, kinetic energy, but it has to come from somewhere since energy can't be created, so that's then the potential energy. Those are the equivalent two ways. And they are very important in understanding the case where we have more than two charges, because then we don't just have this simple expression, and especially the concept that you don't double count is also very important. So let's get to that. So for the case of 3 charges, we want some expression for the total potential energy that's stored in here. So this is the answer we'll get in the notes, just in a bit of a different form sometimes. But so the 0 is just imagining Q1. We just start with Q1 in this case. You can start with any charge. It's arbitrary. The answer will come out to be the same, but we'll start with that one. Now we want to move another charge closer. So let's move Q2 closer from infinity, and we move him in here. Now we did a certain amount of work, which is this Q1, Q2 over R12. We have the extra factor outside here. So that's just the definition for R21 that we for two particles. But now we need to imagine moving a third particle out from infinity into here. So not only do we have to do work that, say all of them are the same charge, pushes against Q1, we also have to do work that pushes against Q2. Or if they are opposite charges here, then the sign of the charges will just make the work the other sign, which handles that for you very nicely. So we need to not only take the contribution from Q1 or Q2, we need to take the contribution of both. So this term is basically just the work that it takes to put Q3 here from infinitely far away. So then you get this. And then you see at the end that what you've done is you've summed all pairs that you can possibly make. Because you can make 1, 2, you can make 2, 3, or you can make 3, 1. Those are the pairs that you can make with three objects. So we just make all of the pairs and sum all of their potential energies up, which we can also imagine for the kinetic energy as that this, as soon as you let go of them, then this one's going to get pushed away by this one, and it's going to get pushed away by this one. So it's just going to zoom off into infinity. This is all of its opposite charges. If it's negative charges, it's a bit more complicated than that, but the intuition stays. So it's going to get, this one's going to give it a push, and that one's going to give it a push. So we need to sum both of its contributions to the kinetic energy, or in this case, the potential energy that's going to become the kinetic energy, and the same for each one of these. Each one is going to get pushed by both other two. So that's why we have Q2 in relation to both Q1 and Q3, just as we have any other one with relation to all the others. So for 4 charges, for example, you'll still just sum all the possible pairs. You can think about it as moving one by one, or you can just think about it like this, where it's each possible pair that you can make and you sum their potential energies together. Just make sure you don't double count, where you have the potential energy from Q1 and Q3 plus the energy of Q3 and Q1, because those two are the same. So just make sure you don't make that mistake.